Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at plate tectonics. So this video is going to correspond to section 3.8 of your textbook, so we're going to think about plate motion now. So the next thing we need to think about is, well, what actually moves the plates? Why do the plates actually want to move around? Now, the plates are obviously have to be moved around by some kind of force. There has to be something that's actually making them go. Now, there are actually three main contributing factors that actually help to move the plates. The first factor is something which is referred to as convection. So the mantle, or most accurately the asthenosphere, is convecting, just like a pan of boiling water. So what we have in convection is we have mantle that gets heated up down here at some deep depth. The hot mantle naturally wants to rise because it's hot and therefore buoyant. The mantle rises, but as the mantle begins to rise, it starts to get cooler. Eventually it becomes cooler, it becomes denser, and then it starts to sink back down. It gets warmed up, it gets pushed back upwards again, and so we have these convection cells establishing themselves in the mantle, where warm mantle rises and cold mantle sinks. Once again, just like a pan of boiling water. Now, these convection cells help to contribute a little bit to the process of plate tectonics. So here we have a situation where we have two convection cells. One convection cell is coming up here like this, so it's circulating in a clockwise fashion, and this convection cell is circulating in an anti-clockwise fashion. So the hot mantle down here is getting warmed up, it's rising, it's cooling, and then it sinks to get warmed back up again, and so on. So this area of mantle here is going that way, off to the left. This area of mantle here is going this way, off to the right. And this means it's naturally going to want to take some of the lithosphere with it. It's just going to naturally, it's not really going to be a particularly strong pull, but it's just going to gently tug on the lithosphere above it, and it's going to help to move it a little bit along with the convection. So as this convection cell here moves this way, it helps to very gently pull the oceanic lithosphere here along with it. And so this is going to be the first of the factors that contributes to the movement of the plates. Now, I need to be clear, convection is a relatively minor contributing factor to plate movement. The other two factors are by far and away the more dominant force. So the other two forces which help to make plates move are referred to as slab pull and ridge push. So ridge push is just exactly as it sounds. We know that at these mid-ocean ridges new crust is being made, and in order to make new crust you obviously need to force a path through the old crust. So you need to crack the old crust open, inject new magma, and that magma cools down to form new oceanic crust. In the process of obviously breaking the crust open to make space to inject more magma, you're essentially pushing the crust apart, aren't you? And this process of pushing the crust apart in very small increments, one at a time, just to make room for some new magma to be injected, helps to essentially, over time, push the crust away. And so every time a new dike gets injected into the ridge, essentially it pushes older oceanic crust away from the ridge. So that's ridge push. Essentially the creation of new crust pushes old crust away from the divergent plate boundary. The other force is slab pull, and this is when we have a piece of oceanic crust being subducted down into the mantle. So what we have is we have a situation where we have a very heavy, dense piece of oceanic crust dropping down into the mantle. So we not only have something that's very, very dense, but it's also having extra force being added to it by gravity. So because it's naturally sinking already, gravity helps to pull it down that little bit faster, and so a combination of weight and gravity starts to pull this piece of oceanic crust down into the mantle. Obviously, as this piece of oceanic crust subducts, it pulls the oceanic crust behind it along with it. So essentially, as this piece of oceanic crust goes down into the mantle, it takes the oceanic crust behind with it on the same journey. Now, that means that ridge push and slab pull are both very important factors in helping to move the plates. When it comes down to it, slab pull is typically the dominant force. So slab pull is what does most of the moving. In some cases, it's been predicted that slab pull could actually account for up to 90% of the movement seen. Now, that's probably a pretty extreme example, but it gives you an upper limit of how important slab pull is. So the movement of the plates is a mixture of ridge push, slab pull, and other lesser forces, of which mantle convection is probably the dominant contributing factor. So here's the diagram we saw earlier, shows the surface of the Earth, and we can see it split up into its constituent plates. Now, once again, we have the arrows here, which is showing us the direction in which the plates are moving, but you'll notice the arrows are slightly different to the ones that we saw earlier. You'll notice some arrows are smaller and some arrows are larger. And this corresponds to the rate of movement. So the small arrows are about 3 centimeters a year, whereas the large arrows are about 9 centimeters a year. And so this is something we need to think about. The rates at which plates are converging or diverging are not constant everywhere. There's lots and lots of variability. Now, this is one of the factors, therefore, that helps to explain the movement of some of the pieces of crust. Because think about it. If all the convergence and all the divergence was happening at a constant rate, it would mean that crust would be being made and destroyed equally fast. And so this would mean the continents would pretty much sit where they are. They wouldn't really go anywhere. However, because the speed is variable, it means in some places subduction is happening very, very quickly, and in some places subduction is happening much more slowly. And so this leads to a net imbalance. And so this means over time, the continents will start to move around relative to each other because we have this heterogeneous distribution of speed, essentially. The rates are variable depending on your plate boundary. And so the fact that some plate boundaries operate faster than others, that's what creates the force that really also helps to contribute to the movement of the continents, or should I say the plates, because there is this imbalance. So the next question is how do we know in which directions the plates are moving? Well, on the whole, it's a relatively straightforward process to work out the direction in which a plate should generally be going. So if we look over here, we have the Indo-Australian plate. We can see that we have a divergent plate boundary running down here. That's obviously going to be pushing in an easterly and northerly direction. And we have a subduction zone running down along here. That's obviously also going to be allowing that movement in an approximately northeasterly direction. And so we know that the Indo-Australian plate is going to be going approximately northeast. Now, in terms of actually getting very high resolution data, though, we have to use satellites. So this map here shows us satellite data, with the arrows show us the direction of movement, and the length of the arrow shows us the speed. So the longer the arrow, the faster the plate is moving. So what you can see here is that in some instances it looks like the arrows are curving. And this is because the Earth is a three-dimensional shape, it's a sphere. And when we try and project this three-dimensional surface onto a 2D plane, like we're doing here with this map, it essentially means the curvature is included in the data like so. And so the fact that we can see the arrows curving is the result of the fact that the Earth is a sphere. Okay, in reality, North America is moving in an approximately westerly direction. As I said, it's just the fact that the curvature of the Earth makes it look like we have this curve, but in reality we don't. So we can see that the rate of movement is variable depending on where you are on the surface of the Earth. So for instance, we can see that the Indo-Australian plate is moving in a northeasterly direction quite quickly. In contrast, let's try and find a better example, the Eurasian plate is moving in an approximately easterly direction more slowly. And of course, this is an effect of slab pull and ridge push. Typically, the stronger the slab pull or the ridge push, the faster the crust will be moving. And that's not really a huge surprise. So the last thing we need to think about is the geometry of plate boundaries. So the thing about plate boundaries is they have to change at some point. And so a really nice example of this is the transition from the Queen Charlotte Fault here, which runs along the west coast of Canada, and its transition into the trench associated with the convergent plate boundary that runs along the south coast of Alaska, and then eventually over along the southern margin of the Aleutian Island chain. And so obviously you can see we have a segment which is a transform plate boundary right here marked in green, and we have the convergent plate boundary here marked in red. Now we know the Pacific plate is moving in an approximately northwesterly direction, and so we know it wants to go this way. And so we know when it hits the continental crust right here, there's got to be a convergent plate boundary there. There's no way around it. It's got to happen. At the same time, we also know that this northwesterly movement means that the Pacific plate has to move past the North American plate, so we obviously have to have a transform plate boundary right here. Once again, can't really avoid it. It's the only logical solution to the problem. Now, where it gets interesting is going to be right here where the two join, essentially. And these areas are going to be quite complex from a geologic point of view, because you have a mixture of different stress regimes. So if you imagine this area here, we have a situation where we have a collision going on. That's going to be a compressional stress regime. The rocks are being squished. In contrast, along here, where we have the transform plate boundary, that is going to be a stress regime which we refer to as a shearing regime. The rocks are going to be stretched in different directions. And so that obviously means you're going to have different regimes overlapping, and so right here it's going to be, from a geologic point of view, absolutely horrible. It's going to be very, very complicated geology in that area. But the most important thing to remember is that this transition in the plate boundary is driven by a change in geometry. So typically, if you see a plate boundary making a substantial change in its direction, that is normally associated with a change in the type of plate boundary. So we can see it here, our plate boundary is moving approximately northwest southeast, and then we are changing direction to an approximately southwest northeast orientation. So as we change from one geometry to the other, obviously that means we are most likely, well, we're very likely to change the type of plate boundary. So when you see a plate boundary changing direction, that's normally an indicator that the type of boundary you're seeing will also be changing. Okay everybody, thank you for watching this presentation and have a good day.